Welcome back to the deep dive. You've brought us quite a stack of technical material today. We're looking at the world of keeping things from, well, exploding or burning down.
That's the goal.
So our mission is to cut through all the engineering specs and regulations and really give you the core architecture of safety and do it fast.
Exactly.
We are diving deep into fire and explosion prevention and protection. And this is not about, checking the batteries in your smoke detector at home.
Not at all.
This is about the deep, sophisticated engineering that's layered into critical structures, industrial processes. We're looking at why systems are built the way they are.
From the passive defenses, the things literally in a building's bones, all the way to these lightning-fast electronic systems that can, stop a disaster in a blink.
That's the full hierarchy then, starting with the static structural things.
Right, things that don't move or need power. Then we get into the dynamic controls for flammable materials. And then finally, the ultimate fail-safes.
The active mitigation for when it's all gone wrong.
That's it.
Okay, let's unpack this. Starting with the buildings themselves. The idea that the structure is your first line of defense. So we're beginning with passive protection. This is the safety that's literally engineered into the building.
Yeah.
Right? It's not dependent on a person or some electronic trigger.
That's the essence of it. Our sources point to four main things that really dictate how a fire behaves.
Okay.
First is just distance from the source, obvious. Second, the materials used to build it. Third is the layout, how it's all divided up.
And the fourth one, which I think gets overlooked, is what's actually in the rooms. The furniture, the decorations.
Exactly. The structure is the barrier.
Yeah.
And the most critical concept here is compartmentation.
Right. So you're dividing a building into these fire-tight cells.
You are. You use fire-resistant walls, floors, doors, and the goal is to stop the spread of fire and smoke. You contain it where it starts.
Buys you time.
It buys you critical time for evacuation, for firefighters to arrive. It's fundamental.
And the rules for how long that containment has to last are super specific.
Oh, absolutely. They're key engineering metrics. For your main fire compartment walls and floors, you're generally looking at a 60-minute resistance rating.
An entire hour.
A full hour where it has to stay structurally sound and block everything. Now, for, say, internal office walls within a larger floor, that might drop to 30 minutes. The risk is just lower.
And that difference, the purpose of the compartment, that's what really stands out to you, isn't it? Because a compartment can be designed to do two totally opposite jobs.
This is where you see the real design philosophy. You have high-risk areas.
Okay.
These are designed to keep the fire in. Think of a boiler room or a chemical storage closet. You want to contain that hazard right there.
Keep a local problem local.
Exactly. But then you have the complete opposite.
High loss effect areas.
Right. And these are designed to keep the fire out.
So this is your server room, your essential records archive.
Critical equipment that you just can't replace easily. The walls, the doors, they're all about resisting an external fire that might be raging just on the other side.
And getting that classification wrong at the design stage could be just catastrophic.
It would undermine the entire strategy.
But even the best walls have holes in them, for pipes, for wiring, for ventilation.
And that brings us to a really critical detail. Fire stopping.
Sealing those gaps.
Every single one. Wherever a service penetrates a firewall, you have to seal it. And it has two jobs, which is easy to miss.
The first one's obvious, right? Stop smoke and flames from just pouring through the hole.
That's the easy one. The second, and sometimes more dangerous one, is stopping conducted heat.
So the pipe itself gets hot.
Red hot. Imagine a big steel pipe running through that wall. The fire's on one side. That heat travels right along the metal, and it can ignite something on the other side of the wall.
The safe side.
The supposedly safe side. Fire-stopping materials have to interrupt that heat transfer.
So how do they do it? What are they using to seal these breaches?
It can be simple stuff, non-combustible mineral wool, baffles, but the most impressive solution is often intumescent material.
That's the stuff that expands with heat.
It's an incredible piece of chemical engineering. It might just be a paint or a caulk, but when it gets hot, say around 300, 400 degrees Fahrenheit, it swells up.
How much are we talking?
Sometimes 50 times its original volume. It foams up, seals the opening completely, and then hardens into this fire-resistant char that restores the wall's integrity.
That is clever. So that's the structure, the passive defense. But when you're dealing with processes, with flammable dusts or gases, you need something more, something active.
You do. When we move into an industrial plant, the fire or explosion risk is often just a symptom of poor process control. You've allowed a flammable mix of fuel and air to develop.
So prevention starts there. with controlling that mixture.
It does. We rely on basic process controls to keep that fuel-air mix outside the flammability limits.
This is a great concept for you to remember. It's like a car engine. It can't be too rich or too lean.
Perfect analogy.
Yeah.
If there's not enough fuel, it's too lean to ignite. We call that being below the lower flammability limit, or LFL.
And if there's too much fuel, not enough oxygen.
It's too rich. You're above the upper flammability limit, or UFL. So a huge part of prevention is just robust ventilation and using detectors to make sure you stay safely outside that flammable sweet spot.
But what if ignition does happen inside a vessel or a duct? The next step is isolation.
Crucial. This is about stopping an explosion from spreading through the whole system.
Because that's how you get secondary explosions.
Yes, and the secondary explosion is almost always worse. The initial blast sends a pressure wave down a pipe, stirs up subtle dust in the next piece of equipment, and then boom, a much bigger catastrophic event.
So isolation is the fire break. And there are two different ways to do it.
Two main philosophies, really. You have passive isolation, which is simpler and, because of that, more reliable.
It's built in.
It's just part of the design. You engineer a mechanical choke into the system. It could be a baffle plate in a screw conveyor or a tight bend.
A physical blockage.
A physical blockage. The most common example is a rotary valve at the bottom of a filter. It creates this tight seal that stops the blast from propagating.
Okay, so passive is reliable. But then you have active isolation, which sounds faster. It relies on sensors and electronics.
It is faster, but you're introducing more points of failure, you know? The sensor, the power, the mechanism itself.
So it's a trade-off.
It is. Active systems use detectors that sense that initial pressure rise in milliseconds, and they trigger something like a fast-acting valve that slams shut, or they inject a dry powder suppressant.
And you'd use that when speed is everything.
When speed is absolutely critical, yes. But if you can get away with a simple passive choke, that's often the preferred choice.
And the physical plant layout itself is part of this defense, too. Our sources mention things like single-story buildings for dust explosion risks.
The layout is absolutely part of the mitigation strategy. One-story buildings make it easier to vent an explosion safely. You also see blast walls.
And these aren't just thick concrete walls.
No, they're engineered to fail in a predictable way, or to redirect the blast wave to protect a control room or another critical area.
If we connect this to the bigger picture, then it all comes down to segregation, right? Keeping things that shouldn't be together far apart.
That has to be a primary consideration. You cannot store your oxidizers next to your fuels. It dictates the layout of the entire site right from the very beginning. They need to be in designated separate areas. And all of these controls, the structural, the process, they all rely on first defining the risk accurately. And that brings us to hazardous area zoning.
This is the regulatory map that tells you what you can and can't do.
Yeah.
It classifies areas based on how often an explosive atmosphere might exist.
Exactly. It's defined by regulations like DSEER here in the UK.
Let's break this down for you because it seems complex, but it's logical. There are two tracks, one for gases and one for dusts. For gases, vapors, or mists, it's about time. Zone 0 is the most hazardous. The explosive atmosphere is there all the time or very frequently.
Right. Think inside a fuel tank.
Then Zone 1 is where it's likely to pop up occasionally during normal operation, maybe during maintenance.
And Zone 2 is the least hazardous. It's not likely to occur, and if it does, it's very short-lived.
And for combustible dusts, it's the same idea, just different numbers. Zones 20, 21, and 22.
It mirrors it completely. Zone 20 is where a dust cloud is present continuously, like inside a silo. Zone 21 is where it might happen occasionally, like around a dusty bagging machine.
And Zone 22 is, again, not likely and short-lived if it happens.
That's the framework.
So once you've defined your area, say you're in a Zone 21, what does that actually demand from you, practically?
It demands the strict exclusion of ignition sources.
Anything that can make a spark.
Anything. If you're in a Zone 20 or 21, your normal cell phone, your wristwatch, a standard flashlight, they're all potential ignition sources. A tiny spark from a circuit is all it takes.
You need special equipment.
You need equipment rated as intrinsically safe for that zone.
Yeah.
It means tough inspection regimes. And it means managing static electricity.
Static. The
Yeah.
invisible danger.
It's huge. We rely on earthing or grounding, making sure every piece of metal equipment is connected to the ground so that static charge from, say, powder sliding down a chute can't build up and create that one tiny spark.
And of course, the human factors. No smoking.
No open flames, no smoking. But it also means you need strict permit-to-work systems. If a contractor needs to bring a grinder into a Zone 2 area, there has to be a formal process. And simple good housekeeping, you can't let combustible dust build up on surfaces.
There is one more prevention technique, a really powerful one, for when those other controls just aren't enough.
And that's inerting.
Inerting is, well, it's the ultimate solution in some ways. You just get rid of the oxygen.
You replace the air with something like nitrogen or CO2.
Exactly. You remove one side of the fire triangle.
Yeah.
No oxygen, no combustion. It's definitive.
Mm-hmm.
But it's usually a last resort.
Why is that?
Because you're making the atmosphere instantly lethal to humans. It's typically only used in very high hazard situations, like inside a chemical reactor, and requires extreme levels of control. So we've built the walls, we've controlled the process, we've zoned the area. But safety engineering always assumes failure is possible.
It has to.
So if every one of those prevention layers fails, and you get an ignition, we are now in the last line of defense, explosion relief. This is pure mitigation.
The game has changed. The goal is now survival, not prevention. And the main technique is explosion venting.
And the principle is simple physics, isn't it? Give the explosion somewhere to go.
A safe direction. An explosion creates immense internal pressure. A vent is just a pre-designed weak spot that will fail instantly and let that pressure escape, ideally up and away from people.
These vents are fascinating bits of engineering. They have to be the weakest point, but only when you need them to be.
Right. And we see a few different types. The most basic are bursting discs.
Just a thin metal circle.
A thin metal membrane, precisely made to fail at a specific pressure. Very reliable, but they're single use. Once they go, you have to replace them.
And for bigger explosions, where the pressure rises much faster.
Then you might use explosion panels. These are often larger, rectangular. They might be hinged, or use a lightweight plastic membrane that just shatters. They're designed for a much higher rate of pressure relief.
But venting just redirects the problem in a way. You now have a massive fireball shooting out of your building.
Which is a significant secondary hazard, and that's why you sometimes see quench tubes.
Okay, what do?
You place them over the vent opening. Their internal structure is like a metal mesh or grid that's designed to break up, cool, and extinguish that escaping jet of flame. It can dramatically reduce the size of the external fireball.
So that's managing the explosion. But the most cutting-edge failsafe tries to stop it before it even really gets going, suppression.
Suppression is a different beast entirely. It's an attempt to abort the reaction itself.
It's unbelievably fast.
It has to be. It uses advanced electronic sensors to detect the very start of the pressure rise. We're talking tens of milliseconds.
That is literally faster than you can blink.
It is. The instant that pressure is detected, the system fires an extinguishing suppressant, usually a dry powder, into the vessel.
And the key is that it gets in there before the main blast wave can even develop.
It stops the combustion reaction dead in its tracks.
Here's where it gets really interesting. The difference between prevention and this final mitigation is just that tiny window of microseconds. That suppression system is in a race against the physics of the explosion itself.
It is safety engineering at its absolute limit.
So we've covered the whole pyramid, a really comprehensive tour of the layers of fire and explosion defense.
We have.
We looked at the static structural resilience, your compartmentation, your fire stopping, then the dynamic process controls, using isolation and staying outside the LFL and UEL.
And finally, that ultimate mitigation with venting and high-speed suppression.
So what does this all mean?
It means that safety in these complex environments is never about one single gadget or rule. It's a system, a layered defense built on the assumption that things will fail.
From something as simple as a choke in a screw conveyor,
to the incredibly complex calibration of a high-speed suppression system. Every detail is there to buy time and limit the consequences.
And here's a final provocative thought for you to think about. We talked about the critical difference between high-risk areas designed to keep fire in and high-loss effect areas designed to keep fire out. What might happen if a crucial data center, which is clearly a high-loss effect area, was miscategorized in the planning stage? If someone accidentally labeled it high risk, that one error could lead designers to build walls focused on containing an internal fire instead of protecting it from an external one, completely undermining the entire defense strategy before a single brick was laid. Thank you for joining us on this deep dive. We encourage you to continue exploring the source materials you share with us. We'll see you next time.